Hi, my name is Gianmarco Iodice. I'm leading the software engineering team at Arm for Generative AI. And today I'm here in Milan to talk about Generative AI at the edge, in particular to explore the real possibilities of GenAI on edge devices. In this workshop, we're gonna learn how to deploy large language models, a smart home assistant, and an audio generation application. So my name is Gianmarco Iodice. I'm leading the software engineering team at Arm for generative AI. In my team, we look at the use cases, the soft optimizations across all the processors developed by Arm. So which means that from cloud to the very edge. And today's workshop will be just about the edge. Okay, I also are gonna have a bit of introduction about edge devices as well. So I have been in this field for roughly 11 years, just working on AI at Arm, mainly at the edge, on CPU or GPU, embedded GPU and embedded CPU in particular. And I also authored the TinyML cookbook. And I really hope that with this workshop today, you're gonna go out of this room with some interesting ideas. This is what I like from you. So you have ideas and you try to experiment, because actually GenAI is not just a buzzword. It's actually something that is happening. It's not happening just in the cloud. It's also happening at the edge. And when we think about GenAI, most of the time we refer to chatbots, LLMs. Oh, this is GenAI. Well, for me, it is something like that. Or fully generated on device without internet connection. Well, today is not going to be a DJ session. I would love it, but it's not going to be a DJ session. But I promise that will also give you the instructions to build such application on generative AI. So let's have a look. I think the most difficult thing for me today will be to use the clicker, by the way. This is the agenda, 50 minutes. In the first part, we're gonna set the scene. We're gonna talk about GenAI, what it means GenAI, why we are having these such big models, right? To at least give a sense of what's happening out there. We are going to unpack one use case, which is actually, which I very like it. Because from the use case, we're gonna discover other use cases, which is the group chat summarization. It's gonna be quite cool, trust me. We're gonna have also a part where we're going to talk about the frameworks. There are many frameworks. And if we are where we are today, is because of the open source contributions. A part will be reserved also to the data types. What data types can we use for generative AI? What data type did we use for generating such audio samples of very good quality? After the first session, we're going to have a 10 minutes break, mainly to think about what we have hopefully learned, but also to connect. I'd like to have your questions also during the session, but if possible, let's keep it for the end of the first part. Then in the second part will be more about how do we deploy these applications. And I will try to do my best to give you some hints about what you can do today and what instructions you can follow and where to find these instructions. So what we won't cover today, no agents, no agentic AI, okay? This is a very, we're gonna be very close to real applications. Not something, oh, it can happen in 10 years' time or maybe next year. This is something that's happening today on your mobile phone or on your DJ console. And we're not going to talk about also LLM architectures. We're not going to talk about how to implement KB caches, but it's gonna be interesting because hopefully you're gonna learn how to deploy such applications. What is that? This is a Gaussian. It's actually the learning experience for today's workshop. We're going to start slowly. We're going to increase the effort. What does it mean? It means that the level of knowledge, okay, will increase a bit. We're going to reach a peak of the effort around the mid of this workshop. Then we're going to go down a bit. So the effort will go down. We're going to talk about how we're going to deploy it. Because actually deploying these applications at the edge are quite simple. Let's set the scene, and as I said at the beginning, GenAI is not just about LLMs, okay? And I want to stress this point because, well, at the edge, there are LLMs, but can we do something else? Of course we can do something else. There are exciting things where you can do it. You can certainly generate sound. You heard about the sounds generated on mobile without internet connection. And why sounds? Well, you can use, if you are a DJ or a music producer, or, well, actually, we had a presentation yesterday, I believe, Aude used some of the samples, right, in your presentation, which is quite impressive. Is also about image capturing, or image captioning in particular. So what does it mean? It means that we want to provide a context about the image that we have captured with, maybe with mobile phone, but also with other devices. Is crucial for some applications, in particular, when you cannot see your image. Can someone tell me where, for instance, you receive an image and you'd like to know what you have there? An example. So why image caption is so important in some cases? I have one, but... Sorry? That could be one, absolutely. That absolutely is very, very important. On the messaging app, have you ever received 100 messages, unread messages, sorry, for a birthday gift? Well, all my friends usually say to me, oh, I mean, you should reply to our messages. Well, I was at work, I could not read 100 messages. Well, but we're organizing the birthday gift for Marco. I said, okay, what did you plan to buy? Well, I sent the images. Okay, but I need to read 100 messages. That is one of the use cases. You can use image captioning to know what they have organized and maybe have a summary, right, of what your friends have discussed. This is another example of generative AI. Math reasoning, this is actually for kids, right? This is something that kids can play with to do math. That can run very easily on device as well. So let's move on and let's talk about edge devices. When we talk about edge, it's not just about microcontrollers. Edge are devices at the edge of the network. What does it mean? It means that are devices extremely close to where the data are generated, or is generated, sorry. Okay? So all these devices are actually considered edge devices. The DTV, the tablet, the large screen computer, which is the laptop, for instance, mobile phones, and of course, all the embedded devices as well. However, although we're talking about edge devices, we're also talking about different compute capabilities. And when we talk about generative AI, it's not just about compute capabilities. It's also about memory capabilities, okay? Because in some scenarios, these models, and we will see in a bit, are quite large, okay? So it's not just about I have these teraops, but you also need to consider, well, what's your RAM availability to run this model, okay? In today's session, we're going to demonstrate some of these use cases basically across all these edge devices, but I'm going to exclude the microcontrollers, okay? Not because I'm not interested, because simply we don't have time. 2 hours is not enough, believe it or not. But there is also an interesting area for microcontrollers, right? But probably I will, if you have questions, I can probably try to give you some ideas. So from data mining to generative AI, and this is very crucial to explain what's happening and why these models are getting larger and not smaller. Who is familiar with generative AI models, by the way, in this room? No one? Okay, one, two. Anyone else? Three. LLMs? Image generation? Well, not many, right? So there are not many people that actually, they are very, this is actually good. I mean, this is good. I really hope actually you can learn a bit from this workshop. So let's talk about the AI evolution, because this will probably explain why these models are getting larger. And this is actually something we have seen in the past, also with convolution neural networks 10 years ago. The past, where we were talking about AI or ML, we were actually referring to data mining. We have a lot of data. Okay, what does it mean, data mining? We have a lot of data. We need to give a meaning to this raw data. Okay, and meaning is, for instance, could be to understand, to classify an image. And based on that, basically you plan your actions, you build your applications. The present is a bit different. Here, we are not giving a meaning to the data, or maybe, yes, a bit, but here we're talking about slightly different. It's generative AI, right? Here we want to generate data statistically, okay, from trained data. Okay, so I'm going to train a model, and I want the model to be able to generate other data. For instance, images, for instance, audio samples, for instance, text. The future, this is my view, might change, might be different, is probably related to the data reasoning. We are able to generate, we're able to give a meaning, then we need to learn how to reason about the data, so how to play in the actions, okay? So why this slide is crucial, we'll explain a bit, but everything changed roughly in 2017 with attention is all you need paper. So when actually there was a demonstration of what LLMs were capable of, generating text. This is just an example. What can you tell me about Livorno? Livorno is a city in Tuscany, blah, 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 and can give you information about it, okay? But GenAI is basically more than that, but at least in 2017, that actually was probably the killer application, I would say, okay? Although nowadays is not just about this. The other concept, if you're not familiar with that, is when I talk about data mining, I was also referring to discriminative AI, which is different from generative AI. So in the past, we wanted to classify things, maybe to detect things, make predictions, and now basically we have something different where we want to generate data using the training data set. What can you learn from these? What is crucial, in your opinion? The architecture is crucial for sure. Data is what makes or breaks your model, okay? If you don't have very good data, no way, you won't be able to get any good models. Data is crucial. So it's still crucial because it was crucial also for data mining. And this is actually the summary of what I have just said, okay? These are some of the applications we have seen in the past with classic machine learning or with CNN, image recognition, of detection, speech recognition, human activity recognition with the accelerometer, for example, microcontrollers. This is very popular. On generative AI, there are so many things happening. Text generation, image generation, audio, well, video as well. Multimodal, model generation, agents, and so on, and so on, and so on. Today we won't talk about video, because video is still An interesting area, but quite expensive. Expensive for the cloud. Try to imagine for the edge. So, the application we're going to see today are these three. Tightly coupled, connected, to build the story I'm going to tell you today. So we're going to start with the group chat summarization because we heard before about some of the things that are required for the group chat summarization. And this use case in particular will be very important to understand the role of specialized models. A concept that for Edge AI is crucial, specialization. Then we will move on to my favorite one. The favorite one is the on-device and fully private smart home assistant. If you have a smart home assistant at home, you know that probably there is a keyword spotting. Well, actually today it can be, locally, it can be more than just keyword spotting. And I have an example with me with Orbit. I will show you Orbit later. And then, well, there's actually probably my second favorite, is the DJ or the music producer. So this is something, it's still do you consider the DJ console an edge device? Well, hopefully yes, right? It's still an edge device. And this is the application where we're going to demonstrate the audio generation at the edge. Oops. So why on device? Well, when you have an Edge AI presentation, you always more or less have this slide. Or because of scalability, because of privacy, because of cost. It's actually true also for generative AI. Okay? Why you want to scale? Well, because you want to minimize, for sure, the data transmission to the cloud. Because what it costs most of the time is the energy consumption. You want to minimize the energy consumption because most of the time these devices are battery powered, right? And so by keeping the computation locally, you basically try to minimize the data transmission, which is quite power hungry. Privacy. Generative AI is built on data, and data is very, very crucial. And nowadays is also a very hot topic. By keeping that local, well, certainly we can address this problem. It doesn't mean that we're going to solve this problem, because by doing the computation locally doesn't mean that your data is secured or private, okay? Well, an example, you can have an edge device, it does the computation locally, but the device can be accessed by everyone. Is the data private? Nope. Cost. Cost because you basically avoid the transmission to the cloud, so you do basically the computation locally. But there is another factor for generative AI that I haven't put on this slide. What is the other benefit? Think about audio generation. Let's assume we are a music producer, okay? And you want to maybe generate a music or create a music with audio samples. How is your workflow? It's not like, okay, generate this music, that's it. It's an iterative process. It's like coding as well. It doesn't stop at the first iteration. You have to try it. You have to generate different samples, maybe 10, maybe 50. And maybe the samples I have generated, oh, I don't like it. Let me change the seed. Because what is cool for generative AI, given a prompt, you can have different audio samples. And this is amazing. I mean, this means that I can have infinite impossibilities also to generate music. If you had to do this iterative step several times, actually it's quite costly also for sending data to the cloud. And for generative AI, this is very, very important. So let's unpack the group chat summarization. This is a summary, let's say a high-level overview of what you have on a messaging app. So you have text, you have audio samples, records, okay? You have images, and maybe someone in the group is also not an English speaker. No way, sei in Toscana? Ci sono stato anche io lo scorso anno. So, no way. Are you in Tuscany? Okay, I was there last year. Well, you have many things, what we usually say, also many modalities, okay? Different types of data in the same context. This can be very long, maybe 50 different types of data in the same context. Then something that we like to have is a summary, right? I'm at work and, well, and I like to, well, what did I decide to buy? Okay, I need to give an answer to my friends. I don't want to read 100 messages. One idea is, well, I can use a multimodal large language model, and we're going to see what it is in a bit. It's a model that takes different input data and is designed or, let's say, yes, trained to provide a summary. This is quite cool and actually very sophisticated. So, but I have introduced the large language models. I know that most of you, well, not some of you are actually familiar with large language models, but what is a large language model? I try to provide a statement, or let's say a brief explanation of what it is. It's still a neural network, okay? But it's trained on a huge data set. It is huge because you need to generate other data. So you need to learn the patterns and generate other patterns. But large language models are built to generate text. Multimodal LLM, this is what I was referring earlier. The multimodal, it is basically something slightly different because it's an advanced large language model that can take inputs of different data types and also generate other data types. Not just text, it can also generate audio, video if you want, images. So it's quite sophisticated. What can you infer from this? Let's try to, what can you infer from this distinction? What can you tell me about the model size?
It's bigger.
Oh, that's true, right? You have, it's very difficult to have, although there is a huge effort, okay, to try to have this model very small, but in the end, the more modalities you want, well, you have also to consider the implications on the model size. From this, probably, hopefully, it will be clear why specialization for edge AI is important. So here is, yes, it's correct. Okay, these are some of these areas, and please, when I talk about large language models or small language models or tiny language models, I'm referring to what we're seeing today. It's all relative, right? So something that is large now can be small tomorrow. This is from 2025 LLMs, and this is more or less the separation between the categories. The tiny is between 10 million, 50 million watt, because I forgot to put watt. Is the train parameters, okay? The number of trainable parameters, actually. So between 10 and 50, we usually consider tiny. Well, tiny is a big statement, but trust me, it's tiny. What kind of application do we have in this area? This can be an interesting area, in particular for toys, okay? Something where you want, for instance, kids to play to learn a language, okay? Can generate text, and you don't need a very sophisticated a language model that can generate Dante poem or something like that. It's a kid. So we keep the context quite limited. So basically, the trick is very simple. We try to specialize the model to a specific context, And here is how we're going to reduce the number of trainable parameters. There are no tricks. Between 50 million and 5B, well, there is a B, not an M, there is the area of small language models. Why is called small? This is called small because this is the sweet area for LLMs that can fit on edge devices. Above 5B, well, there is maybe the 8B, 13B trainable parameters. We start talking about large language models, and here we're talking about 500B. But let's be practical. What's the RAM usage for these models, right? Well, if we consider FP16 as a data type, this is more or less the relationship between the model size at the top and the RAM, the estimated RAM usage. 10 million is basically roughly corresponds to 20 megabytes. Why? Because an FP16 is made of 2 bytes, so basically you multiply 2, but the number of trainable parameters, and you have more or less the model size. And here I'm not considering the actual RAM consumption, because the RAM consumption is given by the model size plus what? Model plus? Anyone?
Operations and arithmetic operations.
The input or the other operation that I need to perform. So, and in this slide, if you're not familiar with open large language models or open multimodal models, there are a few of them that are publicly available, made by with open licenses. You can see that from this slide, between text only and multimodal, you can find probably the difference between these two is the model size. For text only, we can also have quite, what I want to say is small, very small, but at least at 0.5B, so at 500 million parameters. You can find quite a lot of 1B, very important. But for multimodal, which are very, very powerful, it's not super easy to get something small. Okay, and it's normal. I mean, the more we add, the more we have to pay in terms of trainable parameters. Someone could ask, well, why don't we have just spatialized models? So, if we have to pay in terms of model size, why don't we just generate spatialized models? Anyone?
You need a very specific use case.
Sorry?
You need a very specific use case.
You need a very specific use case. The other one? Yeah?
Sometimes you don't know what you need in advance.
Exactly. These two answers are actually complementary. You don't know, and you need to know the specific use case in advance. Yeah?
But Llama is actually doing the same thing, so it's making a general model and then suggest people to fine-tune it for their application.
Exactly. Exactly. But of course, you need to fine-tune it. Okay? So the benefit is that they can give you certainly something that is easy to use. It can cover a wide range of applications because fine-tuning is desirable, but not always possible. And for some developers, they want just something that works out of the box. Okay? So it's always a trade-off. If you want to pay training cycles, specialization is the key. If you want something to work out of the box, the multimodality is probably the best option. Because remember, and we will see this in a bit, when you do specialization, you might need different models as well, not just one. And actually, this is the slide I was referring to. So, group chat summarization, different modalities. At the very beginning, I provided a solution, but I told you is not the only solution. This is one of the possibilities for the group chat summarization with a multimodal model. But considering, for instance, an open model, you probably need a 5B, right? A 5B multimodal. Maybe there are also something smaller, but if you want to consider audio, images, and text, we are in that range. Well, but you can reduce the memory consumption with the spatialization, okay? Well, if I have audio, I can transcribe the audio with another model. An example is using the Whisper Tiny. It's quite small, it's around 40 million, right? Well, if I remove this modality from the multimodal, I can use maybe another multi-modal without audio. And we are going a 3B area. So we have 3B plus 40 million, okay? It's certainly smaller than what we have seen before. If you want, and you are very, you say, well, I want to make it even smaller. Also, the images can be, let's say, converted to text. There are other models. Here I provide an example. It's very old, right? So it's not very popular nowadays. I'm pretty sure there are also other solutions. But you could use a third model to convert the image to a text. And basically, if you have a model to convert audio to text, image to text, well, I don't need a multimodal anymore. I can use an LLM text only. Then we're going to have probably something around 1B for the LLM, maybe something around 40 million for the speech to text. And I can also have something maybe around 100 million, just to give an example, for the image captioning, okay? So these are solutions. It does not exist, honestly, the best overall. It always depends on what you need to deploy the application. What's the problem with the spatialization, in particular with, does it work? Yeah, with this one. I mean, it's not the problem. So how many models do you have there? 3. So in your application, you need to consider also the time to combine all these 3 models together. Okay, so it's something that you need to consider and pay maybe. Okay. So this is a slide that goes back to the AI evolution that I said at the beginning, to basically provide the explanation why these models are getting bigger and bigger and bigger. And this is actually the evolution, okay, that we are seeing since the 1970s. We haven't seen the models going smaller, okay? We are seeing the model getting larger and larger. Although when there is a disruptive technology, is usually, because we have seen at least with convolution neural networks, we also have seen this with LLMs. Usually when we have a disruptive technology in this field, the models at the beginning are huge. But we learn the technology, and what happens, actually, we have something that goes down in terms of model size. An example with convolution neural networks was actually with VGG16 on AlexNet at the very beginning. But after a few years, we had MobileNet. We moved from million, so more than 100 maybe, or 50 million, to something that actually was around 1 million, okay? And actually, this is something that's happening also for LLMs. So why they're getting larger? Because in generative AI, we have the models are trained to perform different things on top of what we had in the past. The actions with convolution neural networks were not actually part of the model. You have the model, the object detected, the image classification, then the developer builds the application on top of that. Now, with generative AI, it's slightly different. The actions can be part of the model. You pay maybe in terms of model size, but this is something new. agents, if you're not familiar with agents, this is actually what's happening. These models are also capable to perform actions. And we will see this in particular with the smart home assistant. What we'll see with the future, well, probably the agent application, which at the moment part and not part of the model, will probably part of the model. We're going to have also the data reasoning. Well, we expect anyway the model to become even larger. If you're not familiar with this concept, engineered and learned by AI, to keep it very simple, before CNN, when we had to perform the image classification, the features, what are the features? For instance, I have an image, but it was problematic for the architectures at that time to extract the features from an image to learn what an image actually contained because of training issues, because of the architectures. So what happened is that we engineered the feature extraction. Very popular at that time was the HOG, the Instagram-oriented gradients, for instance, to try to detect people in an image. With CNN, actually, that was part of the model. Okay, the model was capable to perform the feature extraction, what you need for the input for the model, and the model at the same time became a bit larger as well. Well, this is actually the summary, but this is a summary to explain what we are seeing today, because the challenges that we are seeing today are very similar to what we have seen with CNNs. It's not something new, okay? So models are getting larger, we need more compute or in hardware to deliver. We also probably need a bit more data around availability on board, because these models are getting larger. And I hopefully provide a reason behind why we need more compute up and why we need more memory availability in a bit. So all the challenges that we had in the past about the power efficiency, constrained storage, security, and privacy are the same for generative AI. Okay, crucial is to run these models at the edge. We have seen at the very beginning of this workshop. Hidden use cases. This is a bonus. Speech to text. I was in Japan 2 months ago. Cool trip. I was in a taxi. I'm learning Japanese, by the way. But even if I'm learning Japanese, I was not very familiar with the language, especially, talking to Japan people. But the taxi driver used a device to perform the speech translation. It wasn't a mobile phone, it was actually a device. I never saw that, in particular in Europe, such a device without internet connection. So you took the device, and started speaking. And that speech was translated to English in real time. So it's something that actually is happening right now. So it's not something new. Live transcription of meeting notes, that could be a device, could be, for instance, be used for capturing the meeting notes, keeping private, maybe sending to your private cloud or through your laptop when you have finished the meeting. So there are interesting use cases. I'm pretty sure there are many, many, many more. Do you have any questions, by the way? Go for it.
Around model complexity and the number of parameters, is there kind of like a theoretical plateau at some point where, at some point, once you increase parameters, what you get out of it is just not worth it anymore? Is there a trade-off in it?
I'd like to have a crystal ball. I'm not sure whether there is a plateau or not, because to answer this question, it also depends on the model architecture. we have seen this in the past, as I said at the beginning, maybe the model getting larger and larger, then getting smaller because the architecture was capable to extract the features in a more efficient way. This is something that could happen also now. So if I provide an answer today, my answer will be for sure for the models I'm seeing today. But what I cannot answer is what other architecture we're going to see in the future. So that is the reason I don't have the right answer for your question. Hopefully I explained the reason. Yeah.
You mentioned before that going on edge, for example, on the DJI console, might reduce cost because you're reducing cost per inference, and you need multiple inference to generate your desired output. But I'm thinking, isn't there a trade-off between, like, for example, I can use a more expensive model, but I might need less inferences. It's like, if I get a better result, then I don't need to fine-tune it too many times. I would rather use a better model and use it for less time than use a less expensive model and have to.
That is true. Okay, so you can use a larger model that is capable to generate maybe sophisticated or something. This is actually a plausible scenario. However, how do you measure the quality, especially for a musician or for a producer? Is perception. So even if you have a very good model, what you're gonna have from the model, you don't know it in the end. What I'm trying to say, the same prompt can give you different answers because it's a generative AI. And it might be that the first tentative, you're not happy. You want maybe, okay, let me adjust this. Maybe I want a drum beat rather than a saxo beat, just to give you an idea. And here it's not about the quality. It's about, well, exactly. Yep.
I was wondering about the willing of the companies to go towards Edge AI. For example, Apple. I was wondering if they would like to have their model on mobile phones. Why? Because maybe the weights of that model could be seen by others. The architecture is not something huge, probably similar to other LLMs, but the weights are coming from the training of based on the data of many users, which is proprietary to the company itself. So the others do not have any access to those data. And if other companies could take advantage of this weight to not, maybe Apple would not like to do such a thing. They would prefer to keep everything on the cloud and be safe instead of their models.
So your consideration is if I have a model that runs locally with the weights, it could be that the weights can be accessed, right? What I can tell you is that there is the security and private zone also on the embedded system. For instance, for ARM, it's called the trust zone. So if you work in that area, no way you can access these weights. Only the, let's say, this goes in the private compute, right? So only the app with the right access can access the model weights. So this is a hot topic, by the way, because and this actually goes at the beginning. The fact that you're running locally doesn't necessarily mean that your data is secure or private. But existing devices today, they have capabilities. And there is also an interesting paper from Pete Worden, if you're interested, explaining exactly this. Okay, the paper was about the for video cameras, okay, but the concept is very similar, and it explains, for instance, how you can solve this issue at the edge. Cool. Question times. Time. Okay. What data types do we generally use for LLMs? Who is familiar with data types for LLMs? Would you use FP64? Maybe not, right?
As well as possible, because if you want to reduce the size of the model.
Do you know any data types? That is
FP16 is the normal.
FP16. Someone said FP8.
There was a Microsoft paper from a couple of years ago which was like encoding 0, 1, and -1, and the end was like 1.4 bits per weight. I don't know if that worked that well, but
I'm gonna have a slide. Any others? Any other data types?
Precision.
Mixed precision. I like it.
Integers, optimization.
Integer quantization. 4-bit quantization. Oh, good. Do you see how many data types do we have for LLMs? Many. And you will see also today how many data types that we have. There are the integer quantization, there are also floating point quantizations. But generally, when we talk about LLMs, we consider less than 8-bit per word, okay? So something that is below the 8-bit precision, okay? If you go back to the slide where I talk about the model sizes, 1B for 8-bit quantization will be roughly 1 gigabyte, more or less. If you use integer 4, half of that, 500 megabytes. If I have integer 1, interesting. Someone said it's not integer 1, but actually it's 1.3. Yeah, it's actually true. But let's keep it simple today. So now, and we are reaching the peak of the learning of the workshop, and after that we're going to enter the deployment. Why is the peak? Because here there is a motivation about why we are using lower numerical precision, okay? So this is a super, very, 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 very high level view of an LLM. The LLM is made of 2 phases. The first phase is usually called the encoder phase. The second phase is called the decoder phase. To have the text generation, I hope you are familiar with LLMs, but in short, you have your prompt, you wait a bit of time, then your model will start generating the words or tokens, to be precise, right? The first phase is exactly that. The time you have to wait before seeing on your screen the first word. It's called encoder. This is a phase, what we usually say, dominated by matrix multiplication operations. Please, this is a very simple view, okay? But it summarizes more or less the LLM compute workflow. The second phase, also called as a text generation phase, is a phase where we have a lot of vector by matrix operation. Who is familiar with the concept of compute bound and memory bound? You're familiar? Who is familiar? Please raise your hands. Okay. Compute means that, well, please give me more compute capabilities in my hardware, because I only, like with that, I can go faster, okay? It means that the computation is limited by the computational capabilities of your hardware, of your processor. When you have a memory bound, I'm gonna be limited by the memory bandwidth of my system, okay? The second phase is usually the memory bound phase. The phase where you're gonna be limited by the memory bandwidth. So the tokens you're gonna see on the screen will be limited. So yes, this is a summary of what we have in this computation. So the right-hand side, if you're familiar with matrix multiplication, you have 2 inputs, the left-hand side, the right-hand side. To simplify the explanation, what you're seeing in next slides, right-hand side metrics are the weights. Once you have trained your model, these are constant. The weights are the same between the 2 phases. The orange dot is the left-hand side. we usually call it also the activation or the input, okay? So these two terms are interchangeable. The weights are constant between the encoder and decoder. The orange bit, nope, okay? The orange bit is dynamic. It's something that changes. So that is the analysis. The encoder phase is compute bound. Then we need more max per core per cycle in my, you usually see also the tops, right? The tops in the slide, this is basically that. The decoder phase is memory bound. So then how do you improve the performance? Well, I improve the performance if I can minimize the memory transfers. There are no tricks. Okay? There are some algorithms to improve the text generation, but to keep it simple, that this is the way to go. But there is the other problem. The models are generally very large, right? So we have 5 bit parameters that require more than 5 gigabytes of RAM with Intel, so it's quite important. Therefore, we need to combine the compute and the software, the novel algorithms, the novel quantization techniques or compression techniques. Compression, quantization is very similar in terms of what they want to, what's the end goal is. And that is the reason, and I love this space. There are so many techniques out there, very interesting, that are helping to minimizing the memory transfer. Why integer 4? Why integer 1 or why integer 2? Because for sure we can make the model smaller, okay? But we are also making what? The text generation phase faster, because we are minimizing the bytes transmitted to and from the DRAM. But the fact that, yes, that's interesting, but doesn't mean that I can use these low numerical precision everywhere. Well, for LLMs, these work very nicely, because this is in particular true for large models. There is a lot of redundancy in these models, okay? And LLMs are typically over-parameterized. This is in particular true when you have large models. When you have small models, like less than 1B, numerical precision like integer 4 might not necessarily work well. Not necessarily, I mean, it can work, but certainly it becomes more challenging, okay? In particular, the integer 1. Integer 1 works very, very nicely, in particular when you have a very large models, because you have a lot of redundancy in the model. But if you want to also use these data types, integer 4, integer 8, and so on, there is a technique, not sure if you're familiar with that, is called quantization-aware training. When you train the model, so who actually trains the model, can adapt the numerical behavior to simulate the behavior of the integer 4. So you train your model, but you also train in a way that basically you're saying, well, on device, I'm going to use integer 4. So please consider that these numbers might be in this range. And basically, it adapts the weights to work nicely with these data types. It's an interesting technique, but what you need to consider. Do you have any, what's the drawback? It's very nice, but
There is more computation because you need to quantize and dequantize.
You need to dequantize and dequantize. So this will affect the training time. You will need more training cycles to do it, for sure. But you also need to know precisely what quantization technique you're going to use it. Okay, so that is, I'm going to use integer 4. That's it. So if you're going to change it later, might not work very nicely. Quantization, very core concepts. We are approaching the peak of the learning. Quantization is a compression technique. And when we talk about integer quantization, it means that if we have a floating point array, we try to use integer values, maybe plus a scale and offset. By using the combination of these, we can reduce the size, the overall size for my tensor, my vector, my quantization, my matrix, and so on. And this is an example. If I have 32 values, well, I think between 128 and 40 bytes is something around 3 point something, which is quite significant, I would say. But how many scale and offset do I need? And this is probably the most important thing when the architects of these data types, they need to consider. The two most important quantization techniques are called per channel and per block. And if you are going to deploy LLMs, these two concepts are probably the most important for edge AI deployment, because these will affect model size and performance. Per channel, you have your array, and I have one way is I want to reduce my offset and scale. I want to have the minimum number of offset and scale parameters, okay, to save memory at cost of what? Accuracy. But there is another technique which is called per block, which says, well, I have this vector, or I have these metrics. Instead of using one scale and one offset for either the entire vector or the entire matrix, let me split the matrix in blocks. And each block will have its own scale and offset. Another concept you're going to hear very, very often is symmetric and asymmetric. Symmetric means that offset is considered 0, so you can just use the scale. Asymmetric, it means that the offset you're considering can be non-zero, so you need to also provide it. These two arguments, if you have asymmetric, usually you can also have very good accuracy, but what you're going to pay, you can probably understand what you're going to pay. You're going to pay in terms of compute, right? Because I have more data, but I also need to perform more operations. And it is very simple because if you look at this equation, well, from a computational perspective, you remove the offset, is one operation left, removed. Per block is nowadays very, very popular for LLMs, in particular when using integer 4. But if you want to achieve, or if you want to see the best performance, in general, I'm not talking about a specific IP here, per channel is usually the best, okay? Because you have fewer scale, offset, multiplication, and addition. So this is also somewhere where you're going to see it. Why it is? Because this is also linked to what we're going to see in the second part of this presentation. So per channel quantization is typically used with quantization wet training. You reduce the number of quantization params. So generally speaking, when we use integer 4, we're going to have just 16 values, right? So one way to reduce the accuracy drop is to use the quantization wet training. It's usually tightly coupled. Info per channel with quantization wet training. Per block quantization is interesting because in many cases, you don't need to spend extra training cycle on simulating the integer 4 behavior during the training phase. So, what we usually call it, we can use post-training quantization. I have my great model in FP16. I split the model in blocks. Each block will have its own quantization params. Then it is likely that it's going to perform quite well in terms of accuracy. So, trade-off. No quantization aware training, in some cases, not always, but you're gonna pay a bit of compute, in particular when the block size is small, because it means you have a lot of scaling offset. On the other end, you have the quantization rate training that allows to use maybe the info per channel, great performance, but you also need to know that your target hardware will exploit that data type. Let me see if yeah. I would say 10 minutes break, and we start descending to the second part. So questions break in case you want it. So we resume in. Yep.
Question around the quantization aware training, process quantization aware training.
Yeah.
When you do fine-tuning, do you have to do post-training quantization, or can you also do fine-tuning with quantization aware training?
Okay, so you do quantization aware training, then you apply the post-training quantization to convert the model to integer full. So PTQ is still needed after quantization aware training, because the model will still be maybe in BF16 or FP16, but the numerical behavior will be constrained to the integer 4 computation. Yep.
As noted, we have many different types of quantization. Int 1, 4, 8, FP16, 32, a lot of things we have. And from what I understand, there are generally 2 or 3 types of quantization that are supported by the hardware. So we have GPUs that support FP16 and 32, and then we have CPUs that support int 8 usually. And for the others, we have like NPUs that do some kind of quantization, they support the type of each of them. But going forward, I was wondering if there is a need for a standard way to quantize, because if one wants to do quantization with 1 bit and the other one with 4 bit, the hardware cannot support all of them. You should have a standard way that all hardware are designed for.
Very interesting question. I'd like to have the crystal ball to predict what data type will be the best. It's difficult. It's difficult because, as you also said, these will be influenced by what hardware I'm gonna use in production. Okay. However, what I can tell you, what I believe is key here, is the software programmability. Although you don't have, in some cases, the integer 4 native supporting hardware, but you can still do the computation in integer 8. So what does it mean? It means that the integer 4 is a compressed format. You load the data in integer 4, but the actual computation is performed in integer 8. When you are limited by the memory transfer, it's great. I mean, I load fewer data, I compute in int 8 because it's memory bound, and I'm gonna see better performance. Because anyway, the memory transfer, even if I don't have the native support for integer 4. The examples that we're gonna see, they can work full spectrum, Raspberry Pi, laptop, they do not have integer 4. But what they have, the hardware, in particular the CPU, here we're talking about the CPU, has a software programmability. So in routines, I've written to load integer 4 data and perform the computation in integer 8. Any other questions?
I have a question.
Yeah.
So you're talking about quantization error training. There is another concept of like deployment error training. So I think it's kind of, you're talking about that. So in the sense that your objective is not to quantize, everything. You have this hyperparameter saying, like for example, there was a question about mixed precision. So you have this hyperparameter of like where, the part of the training where is more appropriate to, for example, do, I don't know, FP16, and where is more appropriate to kind of, go to int 1 if possible. So I know it's going to increase your, compute a lot because you're going to have hyperparameters. I don't know if this is something.
So you're saying, so what's your specific question for this?
Is it feasible to basically have more hyperparameters when we are training? So we have a mixed precision kind of scenario, and and we said, I mean, for example, you could say, I have this amount of memory, give me the best model. I mean, that's a very simplistic.
That's okay. This is a good question. So the question is, this is something we have seen with convolutional neural networks, for instance, right? So can I build an LLM in a way that can be deployed on different platforms by using some extra parameters? It is tricky. It is tricky. Not impossible. And we might, for instance, see some solutions like that. But why it's tricky is the training time. So I give you this very simple example. Here we're training on a huge data set. It means that the training won't end tomorrow. Will end in a few months. If we make a mistake by trying to have these extra parameters and the training fails, I lose a lot of money. Okay? So that is the main reason, because the training time is huge. Okay? And we need to be very careful. Of course, there are some tricks to avoid that, to be very careful anyway, to avoid to have to waste training cycles, because of course it would cost. With convolutional networks is actually different, especially for TinyML. Training does not take that long, right? So even if you fail the training cycle, maybe you repeat it and you adjust it and it will work. Here, no worries. We're gonna start, we're gonna do a DJ session in a bit. So, we're gonna be very Swiss. We're gonna start in 3 minutes.
I have a question if you're still taking them, but it's very, maybe it's even philosophical. You even said that LLMs are over-parameterized. In one day we woke up and there was this ChatGPT and it was working miracles. Was there effort to make these maybe mid-range LLMs, for example, taking data, as we did AI 5 years ago, take the data from the group chats and train the model to summarize the group chats?
So you're saying...
Maybe labeling with the big LLM, let's say.
So you have your group chat, you have a lot of data there.
Yes.
So you're saying, if I have this data, can I use this data to train a smaller model, or?
To summarize, yes. But you do the labeling with a big LLM that actually summarizes these group chats.
Okay. What's the tricky aspect with the group chat? The group chat might be part of an end-to-end encryption in the messaging app, right? So this means that the data cannot be really used for training. Thanks a lot for watching. It was absolutely a pleasure, and I hope to see you again.